Today I'm going to be talking about the geomorphology of the Hebron Fault and the implications that it poses for earthquake hazard in stable continental regions. This made up my master's project at the University of Cape Town. Firstly, let me start by introducing the concept of stable continental regions. We're looking at a map of global seismicity here, and you can see that the vast majority of the events are occurring along the tectonic plate boundaries. These are interplate events because they're occurring between the tectonic plates. Although occasionally large earthquakes can occur within tectonic plates themselves in areas that are generally thought to be slowly deforming or aseismic. These areas are referred to as stable continental regions, and they pose a significant risk to seismic hazard assessment largely because the faults that host these earthquakes are either often not identified as being active or have extremely long recurrence periods of thousands to tens of thousands of years. So let's take a look at Namibia. Here is a plot of seismicity in Namibia from 1960 to 2019. The largest recorded event in Namibia was a magnitude 5.1 in 2009. And for the most part, there is not a lot of recorded seismicity in Namibia. So it's definitely one of these stable continental regions. However, the location for my study is, this makes it even more interesting because there is a large paleo earthquake fault scarp located just south of Sesrim in this this is the study area here in this box, which is a 45-kilometer long scarp with an average height of 5.5 meters and reaching a maximum height of about 8.8 meters. The fault itself is still seismically active. Local farmers in the area have felt tremors, and a temporary seismic deployment in 2017 recorded and located 70 events that delineate a clear fault scarp that's dipping at about 55 degrees to the southwest. So if this fault scarp is capable of hosting earthquakes greater than magnitude 7, which is considerably higher than the largest recorded earthquake in Namibia. So here is a closer look at the field area. I studied these 3 segments of the fault scarp, trending northwest, southeast, just starting just south of Sesrim, running through Hebron Farm and Neuhof Reserve. The first paper to really discuss the Hebron fault described it as having a dextral sense of strike slip movement along with normal faulting. This was based on the stepping nature of the segments, right stepping nature of the segments, as well as offsets within alluvial fans that they saw in Landsat imagery. A more recent study by White et al. In 2009 made several field observations. They took 10 theodolite measurements of the fault scarp, and they determined that it was a purely dip-slipping normal fault that had last ruptured since the late Pleistocene. So my study was, what I'm going to talk about today is, firstly, I'm going to look at regional geology and aeromagnetic data to identify the structure that's been reactivated. And then I'm going to get into what my master's was really focused on, which was producing a high resolution digital elevation model from WorldView 3 satellite imagery, and then to use this digital elevation model to analyze the scarp morphology. So looking for lateral offsets like channel offsets, as well as quantify or measure the scarp height in a lot higher detail than previously before. And as well as, and I also did some scarp morphology characterization, and I identified nick points using extracted drainage from the DEM. The main objectives being to constrain the fault geometry and the mechanism of faulting, and to try determine the number of events that are responsible for the current fault expression. So let's take a look at the regional geology and some aeromag data here. On the left, you can see that there are several lineaments that are kind of running parallel to the Hebron fault, and it sort of runs further south. And when we're looking at this data, we identified the second fault, which we've named the Hebron extension fault, further to the south, but that wasn't included in the digital elevation model. And so this structure in the aeromag data appears to be comprised of the Sinclair supergroup, which is a crystalline basement that is sitting below the horizontally bedded Nama group, and which makes up the great escarpment, as you can see here. So using the contact between the Sinclair supergroup and the Nama group, we can get an idea of the geological offset on the fault. And this measurement was taken on the Hebron extension. And we get an estimate of about 110 meters of offset. And we don't really have the timing of when this offset started, just that that offset has accumulated since the Nama group was deposited. So let's take a couple, or look at a couple field photos. So what we see here are two of the fault scarp morphologies that we observed. So this is the center of the fault scarp. We have a very sharp scarp profile, often with almost no rounded crest, vertical to sometimes overhanging face, free face, and what's unique to this sort of morphology is that these that it's highly calcritized. So the quaternary cover that the fault is cutting through is predominantly a calcritized breccia conglomerate, although the amount of calcrete presence in the conglomerates varies spatially. And so further south on the Neuhoff Reserve, we sort of see the intermediate scarp morphology with a much lower scarp gradient, a similar scarp height, and there's a lot less calcrete on the scarp crest up here. So here's another look, same locations, Hebron Farm in the center, Neuhoff Reserve to the south, and we sort of see here the third scarp morphology, which is a diffuse scarp, and this is where there is no calcrete in the sediments. It's kind of just quaternary cover. I wouldn't call it a unit, a rock unit by any means. And so we go from having a scarp that's kind of defined within a 20-meter window to something that's much more diffuse over 100 to 200 meters. So let's take a look now at the digital elevation model that I was able to produce. I was using pan-sharpened stereo images from the WorldView 3 satellite. They have a spatial resolution of, or cell size of 0.31 meters, and we're able to produce a DEM with a cell size of half a meter. And it worked generally very well. There is a couple little issues with triangulation on some of the areas with higher relief, but this is kind of standard because you have shadows caused by the mountains, as well as there are a couple patches that had very poor contrast, and so the feature finding algorithm had trouble allocating points in this area. So we've got a couple holes, but for the most part, we can get good cross sections throughout along the fault scarp, which was exactly what we needed it to do. Let's take a closer look at some of the detail we can make out. you can sort of see a couple of these specks here, which were either large boulders or small shrubs. And again, on the right-hand side, we see an alluvial fan. We can see the change in drainage. And again, some either large boulders or small shrubs. And this area was particularly good for using satellite photogrammetry because there was very little vegetation on the ground. And so it was a great place to test out using satellite imagery to create digital elevation models. So moving on to some of the results. The first analysis I did was looking for channel offsets, so streams that cross the fault scarp, looking to see if there was a uniform sense of offset between on different sides of the fault. I didn't find any uniform offset from the stream channels, and again with the looking at alluvial fans in the satellite imagery, they couldn't find any lateral offsets. So what we're looking at here are just purely vertical offsets, which were taken as cross sections perpendicular to the fault scarp. I took a total of 160 cross sections, tried to space them at about 250 meters apart down the fault, but took a lot of care to make sure that I was measuring the same surface on either side. And if the angles of the landscape differed too much between the hanging wall and the footwall, then those cross sections were excluded. And so this is what these underestimates and overestimates kind of represent. We can see that we've got a single rupture curve that constrains the amount of slip, and we get a maximum slip calculated from the throw. We measure the vertical difference, which we then converted to throw using the angle of the landscape. So then the next part, once I'd constrained the slip distribution, I wanted to see if I could determine how many events had occurred on the fault or responsible for the current fault expression. So here is a little bit of a case study with 3 alluvial fans of different generations, A being the oldest, B intermediate, C being the youngest, to see if the older fan had accumulated more slip than the younger fans. A and B have pretty much exactly the same height. C was a bit lower, but in hindsight, this is just because this alluvial fan is only deposited on the down-thrown block. And so the fan itself is probably actually reducing the scarp height that we measured rather than, and so I didn't take this as any indication that we were seeing more slip in older surfaces. The next thing I did to look for multiple events was to look at nick points. Essentially, when an earthquake happens, a nick point is created in a stream profile, which is the blue line here, and that over time, that nick point migrates backwards, and then if another earthquake occurs, you create another nick point at the fault, which will then migrate backwards over time. And by counting the number of nick points in the profile, you can get an estimate of the number of events responsible for the current expression. So there were only 2, so of the 22 streams that crossed the fault scarp, there were only 2 places that I was able to identify more than 1 nick point. These are the 2 streams that I'm talking about, and they are located right next to one another. And so this C panel here is an interpreted sedimentary package map, or a map of sediments that I made using the multispectral Worldview 3 satellite imagery that we got along with the pan-sharpened imagery. And you can see that both of these streams are kind of sitting within this gradation of contact from this kind of dark purple to a lighter purple. And my thinking is that we're going from this dark purple, which is unconsolidated sediments, to this lighter purple, which has got some calcrete cement between the conglomerates. And so one of the nick points that we're seeing in these profiles is a geological nick point. So you're kind of dropping through the capping calcrete conglomerate into the soft sandy sediments, and that another of the nick points is the tectonic one that we saw on all the other fault profiles. Oh, sorry, stream profiles. So then the next thing we did, which to identify whether Hebron could be a single event, because all of our analyses up to now had kind of suggested that we weren't finding evidence of multiple events. So we had to ask the question of whether it was whether a single earthquake could be responsible for producing this fault scarp. So what we've plotted here is a whole bunch of slip to length ratios from the literature. So the gray triangles are from the Wells and Coppersmith compilation. The white triangle, white diamonds are from several earthquakes in in Australia. And then we have the Balilam Takataka fault in blue, the Egindava fault in Mongolia in yellow, and then Hebron, different scenarios in red. So what I'm really interested in is the average displacement. So if this was a single earthquake, so n is equal to 1, then we'll be plotting well above the regression line that Leonard calculated for stable continental region earthquakes. And so the solid line is the regression line, and the dashed lines are 1 sigma uncertainties. So this kind of slip to length ratio is very high and is unlike other observed slip to length ratios from around the world. It's true that intraplate events often have higher slip to length ratios, but this seems to be a bit higher than what one would generally expect. And so if you look at the other scenarios for 2 or 3 events, then we're sort of getting much closer to the stable continental region regression line. And so it's probably most likely that the fault scarp was produced through several earthquakes, but even if it was 3 or 5 events, there would still be magnitude 7 earthquakes, which is much higher than the highest recorded earthquake in Namibia to date. So what could be causing this this deformation? Well, this is a quick plot of the gravitational potential energy calculated from the crustal thickness in the area. And so the Hebron fault is sort of sitting in this central region here on the edge of the great escarpment, and the thicker layer of the great escarpment is kind of driving an extension throughout the region. And so it seems likely that the NAM shear zone that I discussed earlier was kind of an older structure that was preferably oriented to be reactivated given the current stress regime that we're observing here. So to conclude, we've got a predominantly normal fault scene paleo fault scarp in southern Namibia that's following an older structure. And we've found no evidence for multiple events, although the implied slip to length ratio is very high, even for other stable continental region earthquakes. So it likely represents a small number of magnitude 7 earthquakes that have occurred sometime since the late Pleistocene. Future work includes trying to get a better bracket on when the last rupture events did occur. Thank you very much for listening. Yeah. And I will stop the share and stop.